Excuse me, sir. You are on mute.
Oh, yeah. Hello. Is it now fine?
Yes, sir.
Yeah, yeah. Thank you. Thank you for. Okay. So now what we notice is in our. I am just recap. I'm doing a recap of what we have learned right now until now. So the output capacitance is a sum of the load, the internal capacitances, and the parasitics. Okay, that we have seen already. So since we are considering the switching aspect of it, okay, how it goes from high to low and low to high, we have to incorporate the capacitance, output capacitance. Otherwise, we will not be able to capture the delays and all that. Okay. So, and in our previous lecture, we also saw the concept of no load conditions, right? So when we are speaking about a resistive load, no load essentially means infinite resistance, RL. The same thing is true for the capacitance also. That means if it is no load, the resistance offered by the capacitance is infinity. Okay, that means 1 upon j omega CO will be infinity. That means CO will be 0, irrespective of the omega, that is the frequency. Okay, so that means irrespective of the frequency of operation, this is going to offer an infinite resistance. So that's how CO becomes equal to 0 theoretically. All right, so what were the assumptions we saw? Number one, Vi was instantaneous. So that means at t equal to 0, Vi responds immediately. Number two, second assumption was that the VO starts responding to Vi immediately. Okay, so there are no violations, static timing violations. Okay, that's why no STA involved are necessary. Okay, then what did we do? We began with uh, the situation when the Vi was equal to VDD, when Vi was equal to VDD. So that means this is the case we are essentially looking at. Okay, so Vi, as you can see, is VDD. Okay, so the output is going from high to low. Okay, so that means it is a high to low means falling. I mean transition. The output VO is falling from high to low transition. Okay. Okay, so we did all these calculations and we figured that this is the uh, expression for the VO varying with time t. Okay, now this is to be noted that the current which we found out, first of all, you notice that the VDD, if Vi is equal to VDD, obviously this P MOSFET, okay, that is going to have a VSGP of 0, which is less than the mod of VTP. That means this MP will be remaining switched off. But uh, MP will remain switched off. That means this entire situation boils down to this scenario. Okay, because the upper MP part is not there. Okay, so now what we will do is we will try to find out at under what conditions. In that case, what first of all, the initially VO was VDD. Notice VO was initially VDD. From VDD it is going to the ground. That is the high to low transition, right? So if it is high to low transition, so initially VO was VDD. Okay, now if VO is VDD, that means what is the VDSP? VDSN? VDSN will be simply VDD. Here I have written that. Okay, whereas what is the value of VGSN? VGSN is, as usual, you can see Vi. Vi is VDD anyway, correct, as we have seen over here. So Vi remains VDD throughout the transition. So if Vi remains VDD, so this will be VDD minus VTN, and this is VDD. Obviously VDD is greater than VDD minus VTN. It means that Mn is in saturation. Okay, the problem is when I said Vi is equal to VDD, that was when I said VO was equal to VDD. Notice this is something to be understood very carefully. This is VDSN, right? But remember, VO value is decreasing like anything, right? So VO will not continue to be VDD forever. Vi will continue to be VDD because that is under our control, correct? So initially, as I said here, highlighted initially, VO is VDD, so VDSN is VDD, perfectly fine. So initially, MN, that is the N MOSFET, begins in the saturation region. However, very soon, what will happen? VO will fall, this blue line, VO will fall below this VDD, VO will not be greater than VDD minus VTN anymore. What will happen? It will go into linear region. Okay, so that condition we also figured out last class. When does Mn go into linear region from saturation? When this VDSN becomes equal to VGSN minus VTN. So this is the case. What is VDSN? VDSN is actually VO, right? Initially its value was VDD. Huh. So the instance when VO becomes equal to VDD minus VTN, that instance I am calling it TB. That is the linear saturation boundary time. Linear saturation bound, when the N MOSFET reaches the linear saturation boundary. So I've got written TB, B for boundary. So if I put this VDD minus VTN expression, this VO equal to this, I will replace this VO with this VDD minus VTN. What will happen? Just little bit of calculation, and TB, I get the expression for the TB. So that means this is the instance for linear saturation boundary. So that means in this transition, if you notice, initially VO was VDD. Later on, it will start decreasing from VDD, right? So there will be a point when VI is basically VDD here. So, as you can see, this is at the same level VDD. Minus VTN. Okay, so that instance I will call it as TB. Okay, so now that instance I'll call it as TB. So let me just draw that, it will be easier. So let us say here, okay, at this point let us say your VO becomes equal to VDD minus VTN. So here I'll put VO equal to okay. So from this point to until this point, Mn was in saturation, and in fact you will notice that this is the point where the current is decreasing, like voltage is decreasing like anything. Why? It is very sharply the VO is decreasing. What does it mean? That the current is very high. The current is the saturation current. That is the reason why it is sharply decreasing. Beyond that, the N MOSFET is gradually becoming more and more linear. So that means the current starts decreasing. And the current starts decreasing means it will take longer to go to the zero. Okay. So now what we understand is, so we have obtained the value of the output voltage as a function of time t in the saturation region. But yeah, this yellow part we have seen. Now what we will do is, we have also found the value of TB. Then after TB, this is the part which is our class today. So after TB, that means that after the linear saturation boundary instance, the N MOSFET comes in the linear region. All I'm going to do is just notice this relation minus CO dVO dt. Why am I calling it minus? Because it is basically the current which is flowing out of the CO. In fact, if we go by the direction of the current, we could have also written CO ddt of, look at the current direction, this from here to there, that means 0 minus VO. That is how you get minus CO dVO dt. Okay, so once you have got that, so this is the discharging current of the output capacitance, and the discharging current will be equal to the linear expression for the current. Okay, that's all I have done. Okay, so here what I shall do is, I'll bring this to outside because I'll say this beta n will be equal to mu n cox by 2 w by L. Then instead of putting beta n by 2, I will just bring the 2 outside. That will become mu n cox w by L by 2. Okay. The same thing here. I mean, I'm just reducing the number of terms and all that. Okay. Here it is. Okay. Then we will just carry out the calculations here. Okay. So where is it? Check it. So this is the okay. So what is VGSN? Look at it. VGSN is VDD minus VTN. So that's what I have written here. VDD minus VTN. What is VDSN? Is obviously VO. Okay. VDSN is here. VO. Okay. I'll put it there. Is equal to this. Then beta n by minus CO TB to T. Why is it TB? Because this is basically only for the saturation region. So only for the linear region. So this is the from this point until this point we are having Mn in linear region, right? So from TB to some point in time T, we will find out the TPLH and TPHL from here. TB to T, and here what is the case? DVO by VO twice this. Okay, then this is T minus TB, there is no problem. Here 1 upon, what I shall do here is that I am going to write like this. I can basically put it VDD minus VTN VO as a function of time T plus VTN notice if I can, this is the partial fraction basically. So what is the case? Twice VDD minus VTN minus VO plus VO. So VO will cancel. The only thing is in the numerator you are going to be left with twice VDD minus VTN, which I will make it the denominator, so that the left hand side and right hand side of these are equal. Okay, so that's what I have written here. Okay. The only now this twice VDD minus VTN outside, I mean on the left hand side of the integral, because it is a constant. So you are left with these integrals. Okay, so this twice VDD minus VTN, this 2 I shall put it here. Okay, and here I'll put it ln VO by VDD minus VTN minus ln of this whole thing. Remember there is a minus, so I'll put the minus here. Okay, very simple integral. So ln VO by this is minus, so that will become inverted. Okay. There will be a 2. Okay, so since this is ln, I'll put exponential e to the power natural logarithm. Okay, so this is, so VOT becomes equal to twice VDD, and if you do the this will be a 2 over here, and you are left with finally this equation. In the textbooks and most of the other VLSI design courses, professors will usually just share the final expressions. I am showing you how to do the integral for each and every step. Okay, step by step integration, how it is coming. So here we find that you are left with this is the tau n. So this tau n is coming over here, correct? So it is just an easier way of writing it. But let us understand What does it imply? Notice that this tau n is in the exponential term, right? So this is basically the discharge time constant. This is the whole thing. Whatever we have done, it is that TPHL, high to low transition का time निकाल रहे हैं, है ना? So this is basically an RC kind of thing. This is CO, and this is the resistance which is offered by the N MOSFET during the transition. So initially that resistance was because of the uh, saturation region, which was very high. Okay. Now in the linear region, this resistance across the N MOSFET is going to be much lower. So the time constant will be different. Okay. So if you, I mean, although it's not very evident from the curve over here, okay, but always keep in mind that before this linear saturation boundary instance T equal to TB, it is initially, what form is this? This is a parabolic one, square relation, okay? But after it goes into the linear, it becomes an exponential. Notice there is T minus TB involved over here. What does it mean? It is just like a, I mean, the origin is shifted from T equal to 0 to T equal to TB. होना ही है, because from T equal to TB onwards, it is linear. From 0 to TB, it is saturated. Everyone with me, right? Until now. So, once we have got, so we have essentially this, ended up in two different expressions or two different functions for the output voltage. One is the parabolic one in the saturation region before the linear saturation boundary T less than TB, and it becomes a different exponential variation when the Mn is in linear after the linear saturation boundary. T is greater than TB. Okay, until now. So what we will do is I will now share with you the second part. Okay, so we have already seen all this. Now what our objective is, I'll just open this one also. Right. So now what we are trying to find out is, suppose we will consider that VH is the voltage which we'll consider as a high voltage from VH to VDD. Okay. And suppose I allocate another voltage which is VL, that is the voltage low. So any voltage which is VL or lower than VL, that means 0 to VL, we will call it as logic, low logic basically. And this is the high logic. Now let me write it here. This is the high logic, this is the low logic. Now something very interesting is that in our VTC, in our voltage transfer characteristics, remember we said, like, if we have, when we were dealing with the VTC, we have the noise margin, right? So noise margin mein, we had the noise margin high and noise margin low, correct? So Remember, how is this high and low variation related with the noise margin? Hello? Hello?
So like as like these variations, if they are less, then the noise margin will be higher.
So in our discussion, remember we had this, no? VO, this will be VDD. Yeah, as you can see, this is VDD and this is our zero. Correct? Everyone, listen carefully. All I'm suggesting is this VO from here to here, VH, we will consider as logic high. And the VO less than this is logic low. ओके तो यहाँ पर नॉइज मार्जिन कहाँ से था remember that the noise margin was defined not with VDD or zero. The noise margin was essentially defined with respect to this part. This was how much? This is VIH and this is VIL. So this was our noise margin. So this was NML. This was our NMH. Remember? So any voltage which is higher than VH, it is definitely, I mean, it does not fall in the noise margin. Because anything, if the VO is higher than VH and if the VO is less than VL, it is definitely logic low. उसमें कोई tension है ही नहीं, like there is no confusion about this, right? The confusion or the dilemma happens only when when the voltage becomes lower than VH or higher than VL. Then it falls under the noise margin. Got it? So if you notice, I wrote VI over here just to show that VI curve. As you can see, this dotted line, this is the VDD basically. Okay. But apart from that, this blue line is actually the VO. Okay. So in this curve, we are essentially trying to concentrate upon the variation of the output voltage VO with respect to the time t. If this curve doesn't include the variation in VI. VI is, as I said, VI is perfectly like VDD here during the transition, right? So basically noise margin is like that. So whatever voltages we are talking about, which is like the ideal one. In case of noise margin, what we saw is that the VOH, okay, the VOH was supposed to be very close to VDD. VIL is supposed to be very close to zero. Yes or no? Okay, but then where is this VH and VL is coming from? That VOH and VOL, which will be somewhere here, this will be your VOL in our noise margin analysis. See, I'm now trying to sorry, this is VOH, this is VOL. I am trying to correlate the noise margin curve with respect to the switching. Okay, so this is VOL and this is VOH. VOH will be very close to VO. VOL will be VOH will be very close to VDD and VOL will be very close to zero. Okay. So this VL and VH is essentially something which we, the engineers, will decide. Okay. So this VOL and VOH को फिर हटा देते हैं. Okay. As you have, all of you have done the VLSI design course, you will remember that in industrial standard we take 0.9 of VDD. That means this range of the range of output voltage which we consider as logic high, we will only consider as 10% of the VDD. Right? Similarly, here is it's also 10% of VDD on the lower end we'll consider as logic 0 or logic low. That's why we used to take 10% and 90%. So that's why we say that what is the TPHL, high to low logic transition में हम 90% to 10% of VDD क्यों सोचते हैं? First of all, ये 90% or 10%, it is the thumb rule, like that is the industry standard. There is no reason for you to say that okay, we have to take. I mean, that is how we define it. Now, interestingly, in certain applications, you might be even more rigorous. Okay, where the logic should be various. So in that case, instead of 10%, I can even say that okay, I will be considering in my particular application for my own particular IC, where we cannot afford any errors, I will put VH and VL to 5% of VDD. Okay, then it will become 0.95 VDD here, and this is going to be 0.05. Okay, so unless it is specifically mentioned in the question or mentioned in the problem, whether it is 5% or 10% or 15% or something, you always choose 10%. So now, since the industrial forum, industry in general, they have accepted this 10% of VDD variation. Okay, that is the reason why when we are comparing 2 or 3 different ICs and we want to find out the delays, okay, rise time, fall time, delays. In that case, what we will do is we will go by the 10% of all the ICs, and then we can have a fair comparison. So some of you will do it at 15% and some of you will do it 5%. The student who will do it in 5%, obviously we will see that the rise time, fall time will be less for them. Okay, so just to standardize everything, industry has decided that it will become 10%. So please remember, this VH and VL values are something which we engineers have decided. Okay, very good. That is international standard basically. So this VH and VL are 0.1 and 0.9. Okay. Now, once we decided on this 0.1 and 0.9, we could actually reach these analysis, whatever we have done, in a much simpler way using the RC network. But instead of RC network, as you can see, we are trying to find out the exact variation of these things. So we will look into that industrial standard definition probably in the next class. We will not be able to finish it today. Industrial standard variation, and why it is industrial standard variation is what we will find out. Okay, you will notice that the industrial standard is actually much simpler to calculate than the way we are doing it. By the way, these calculations were done in VLSI design. Hello. Hello.
No, sir, no.
So how did you learn this? How did you learn this? Only the final results were shown? Yeah, unless you tell me, how can I? Hello?
This approach was not shown, sir.
So what was shown over there? The RC value was shown?
Sir, only NMH and NML were only result were shown only.
Only the results, final
Yes,
results, huh?
yes, sir. For NMH and MLL, not these, sir.
But NMH and ML तो वो तो noise margin है.
Yes,
This
sir.
is
Only up to
totally
that,
different.
sir. Only up to that, sir.
Noise margin has got no, as I told you, this is the noise margin. है ना? ये तो noise margin है, वो तो already we have covered it in the, I think 2 classes before, right? This is very important. Why I'll tell you. Later on, I'll be very honest that I'm doing the difficult approach first. Later on, I will show you the very simple trick. Okay, that is the industrial standard. For example, this is an industrial standard, 0.9 VDD, 0.1 VDD. That is 10% of VDD variation we will consider as the logic high and logic low. Okay, but one thing is that along with it, see, industry is all about making the circuits work perfectly well. They are not bothered about so much of calculation. Why is this calculation necessary? Because once you have this calculation in mind, then suddenly I tell you some new device, some new circuit, then with these fundamental concepts clear, you can actually find out and calculate all the timing expressions for any circuit possible. ठीक है, देखो हम यहाँ पर इन्वर्टर से काम कर रहे हैं, राइट? वी आर डूइंग इट विद इन्वर्टर. So what is important for us is that given any circuit, all I have to do is I will just convert it into an equivalent inverter. Then all these things will be perfectly valid. Now later on we will see an easy trick to do it, but it is going to have some errors in it. But that error will be actually helpful for your designs. ठीक है, जो हम अभी कर रहे हैं ना ये accurate है. We are minutely, meticulously finding out at which point between T1 and T2 we are essentially reaching this TB, which is a linear saturation boundary. We are finding out explicitly, and from there we are calculating what is the time. So this, what is the high to low time? So from here to here is the TB, that's for sure. From T to this one is the time which we have to find out. Okay, we are trying to find out the exact variation of this. Remember, these equations are what is running in your cadence, but they are solving it numerical methods. Okay, but we are doing it analytically. Since we are doing it analytically, it will be difficult for you if the we are excluding some of the finer kind of accurate, the finest details over here. Okay, whereas cadence will take care of all the finer details of the device, and then basically it will work out. For example, यहाँ पर हमने क्या लिया है? If you notice, this is the current in the saturation region. So there is this 1 plus lambda VDS term missing, right? है ना? Just see, this is the expression for the current in the saturation region. So saturation region में तो 1 plus channel length modulation भी आएगा, है नहीं? Like I have shown you, this is only one. There are many other factors also which cadence will take care, or spice will take care, BSIM library will take care, which we are not taking care of. Okay, so of course, so why are we doing this exercise, this tough exercise of calculating minutely each and every point? Because we have an idea how this is working. So 10 years down the line, if you become an R&D person in industry, okay, you are working for Cadence or Synopsys or these kind of companies, or Intel, Qualcomm, whatever. Over there, you have to design a circuit on your own. Then you know that, okay, Surya sir showed us this way. All you have to do is, instead of putting this one, I have to add the channel length modulation and other finer terms also. ठीक है ना? But later on, I will show you that what industry does. This is something similar to the very basic concept. For example, the PMMD students will know this. This is your ID VGS characteristics, right? So this is what we will call it as a threshold voltage, the point where the current starts rising. But remember, ऐसा नहीं है कि below VT this current is zero. No, that is your BTech concept. As I have been telling you many times, the current is not zero. The current is exponentially less. So that means current is decreasing in an exponential manner. So that means this is subthreshold leakages and all that. Okay, so this is VT. So how do you calculate the value of VT here? So what you do is, you take the GM of this curve. GM is what? Derivative of del ID with respect to del VGS. Okay, so you will actually get a curve like that. So this is your GM curve. The point at which the GM is maximum, we define it as the VT, threshold voltage of the device. Okay, and why are we doing this? Maximum GM point as a threshold voltage. That is basically, I mean, that can be mathematically proven that the maximum GM will occur when the current is essentially moving from subthreshold conduction to drift conduction. So after threshold voltage is, after VGS reaches threshold voltage, what happens? The channel is formed inside the device. Okay. Now the device is something like this. The channel is already there. So if the channel is there, then whatever voltage you are applying here, so this is VDS, right? So, sorry. So whatever VDS you are applying, so the electrons will move from the source to the drain. Nice, cool, no problem. But after the channel is there, so that means if the after the channel is formed, the electrons are moving from the source to the drain, thanks to the lateral field VDS due to threshold due to the VDS voltage applied bias. Correct now? So that means when the electrons are moving from the source to the drain through the channel means the road is there, so now you can drive your car. Simple. So why are you driving your car? Because there is some attraction, some movie is going on, so you are driving with your car. That's it. Okay. So you have got, or you are driving your car to the airport because you have to catch the flight. Okay. So once the Shamirpet highway is there, you are going to take the car, right? So that Shamirpet highway is the channel, and your car is basically the electron. Okay. So what is the VDS? You have a plane to catch. So now what the funny thing is that this propagation, thanks to the electric field, is called the drift. Our PMMD students are experts in this by now. So drift कब शुरू होता है? After VT is reached. Okay, so drift happens after VGS exceeds threshold voltage. Okay, I'm digressing a little bit so that you understand the difference between the analysis that we are doing and what industry propounds or kind of promotes. One is the industrial standard, one is theoretically accurate one. Okay, now this is a very interesting concept, by the way. So this is at the device level, this is at the circuit level. Okay, so this is what the scenario is. Now before the channel is there, that means in the subthreshold conduction, before VGS is VT, क्या होगा? Channel तो नहीं है, ठीक है? Then how will the electrons flow? The electrons will flow due to diffusion, because diffusion is a process which is always there. What is diffusion? Diffusion is simply that it's like that perfume bottle experiment which we have studied in our school days. Remember, you keep an open perfume bottle in the one corner of the room, the whole room now smells of that perfume, right? The more you go towards the perfume bottle, the more stronger will be the smell. Okay, so that means it is nothing more than higher concentration or lower concentration diffusion. Okay, so this N plus region, this is the source. This source is having full of electrons, N plus, right? That means full of electrons. This is P substrate, less electrons. So the electrons will simply diffuse even if you are not putting a VDS batch. So this is the process of diffusion. Okay. So this is a diffusion is the main cause of the subthreshold conduction. Okay. Now it turns out that in the subthreshold region, as I said, it is an exponential current is an exponential variation, but it is much lesser. So that is the reason why you don't see any current in the linear region, in the linear range. Okay. Whereas in case of GM, it is also going to be exponential. Remember that ddx of e to the power x is e to the power x. So that means in the subthreshold region, if the current is an exponential function, the derivative of that will also be exponential. So GM is exponential in the subthreshold region. Later on, we will see, as I am always repeating, subthreshold region is the perfect saturation region. The only thing is that the currents will be very less. Okay, so if you are not concerned about very high current in a particular application, you should always try to go for the sub-threshold designs. Anyway, so GM is exponential, so that's why it is very sharp. And after VT is reached, what will be the GM? This is something which you all know, twice ID by VOV. Correct? So it will essentially be a smoother curve like this. However, the maximum of GM will occur at the point of VT, wherever there is a shift from the diffusion transport to the drift transport. So wherever there is a whenever there is a shift from the diffusion transport to drift transport, you are going to have the threshold voltage. This is how the accurate one is. अभी industry क्या करता है? As you can see, finding out the GM and then उसके बाद you draw the GM, find out where the maximum point is, then find the VT. It is too much time for the industry people. What they'll do is, remember in this course also we have seen that after VT the device will be operating in the saturation region. ठीक है? So ये VT है. What is this value? VDS plus VT. This is the saturation region, correct? उसके बाद है linear. We have also shown this through our Python code also, right? So if this is the linear one, all industry will do is they will, if this is the linear part, they will simply extrapolate and find this point wherever this tangent of this, I mean tangent क्या, ये तो linear ही है, wherever this line in the linear region is crossing the VGS axis. इसी को industry VT dash बोल देते हैं, VT dash कहते हैं. That is the threshold voltage. That is how industry thinks about the threshold voltage. Okay, now let's forget about all the rest. All we are suggesting is that we are kind of increasing the threshold, actual threshold voltage is here, industry related threshold voltage is here. So this shift, is it a good thing or a bad thing? It's a question to you. PMMD students, think like an engineer. Threshold voltage बढ़ गया apparently, तो ये अच्छा है या बुरा है?
Sir, from leakage point of view, it is good, sir.
Yes, leakage point of view it is good.
Because the diffusion current is less.
Absolutely. हाँ, yes, diffusion current तो है. Yes. What else? From the kind of operation of the, let us say, inverter itself, how does it go? Yes, of course, leakage is definitely less. This is obviously, you can call it as the overestimation of the threshold voltage, correct? Threshold voltage actual is here, मतलब यहाँ से यहाँ तक. Now you are overestimating it from here to there. From leakage point of view, of course, that is less.
Power consumption would be high, sir.
Obviously, that is also power high.
Means increases, na, sir.
See, the leakage power to kam hua, definitely, as your friend has rightly said. So the situation is something like this. Initially, it was like that. Now, it will be coming from here as usual. It is now like this. So basically, clearly you are reducing the off current. See, what it does is, if you are making a circuit with this, with an overestimated threshold voltage, okay, by the way, PMMD students, hello, all of you are here, right? What is the effect of temperature on threshold voltage? Hey, come on, I taught you for the whole semester. What is the effect of temperature on threshold voltage? Does it increase or decrease?
Increases, sir.
VT increases with threshold voltage. Think.
Sir,
Decreases.
inversely relation, sir.
It decreases. Okay. So what does it mean is that if I am having the original threshold voltage here, original one, I am not overestimating or anything. ठीक है? Exactly जो device में आता है वही हमने लिया. Now you started watching a long movie of 3 hours. A 3-hour movie, 2.5-hour movie. Very old movies are like that only. Okay. So if you are making it like 3-hour movie, what will happen? Your laptop is becoming hotter. Your IC is becoming hotter. What will happen? Your threshold voltage will keep on decreasing slightly. So after 2 hours, what will happen? Your threshold voltage has come here. So what will be the leakage current? It will come here and like that. So the leakages will become very high. That is the reason why you will notice your laptop becomes hotter. है ना? आप clearly समझ पाओगे. In fact, सुन भी पाओगे. Like your laptop or your desktop is making sound, right? After 1 hour, 1.5 hour, old laptops and all that. ये sound क्यों आता है? What is the sound you hear when your laptop is very hot? This is some practical question, यार. There is no theory. There is no engineering here. आप किसकी आवाज सुनते हो?
The thermal fans.
हाँ?
Thermal fans.
Fans, exactly. That means your laptop fans are doing overtime because your laptop has become so hot, it is trying to reduce the heat. It is the sound of the fans which you are hearing. That is the reason why all the servers which have to work 24/7, so they are always kept in the AC rooms. Your laptops, computers will always work better under colder temperatures, colder weathers. Okay. Why? Because your threshold voltage decrease will not happen. You are trying to stop the reduction in the threshold voltage because of temperature increase. But now, when Intel is making one processor, ठीक है, आप एक प्रोसेसर डिजाइन कर रहे हो, उसमें आपने you took the exact theoretical value of threshold voltage with the maximum GM point as I have shown you. What will happen? Initially it will work fine, but after half an hour, your fan will start working overtime. There will be a lot of power consumption. Okay. So what industry needs to do is they need to ensure that at least you should be able to, the battery should last for at least 2.5 hours or 3 hours when you are purchasing a laptop. So what they will do is, instead of using the actual threshold voltage, they will estimate how much of reduction in the threshold voltage will happen and how much of off current the CPU can still kind of survive, let us say. It can still withstand. Okay. So what they'll do is they'll rather overestimate the threshold voltage by a certain amount, so that even if you are watching, say, a very long movie, what is that? Sholay is also like 3-hour movie. Okay, अगर शोले देखना चालू करोगे ना, बीच में वो हीरो कुछ कहेंगे, and then it will be your laptop will be shut down because it is overheated. Then you will get angry with Intel making a very bad processor. So what Intel will do, they will overestimate the threshold voltage a little bit, such that even though you are watching a 3-hour Sholay movie, it will still be able to withstand that reduction in the threshold voltage. Okay. Now, with overestimation, आप कितना करोगे as an engineer? Industry people thought, don't bother. You will simply take the slope in the linear region. So that's why they will choose the VT dash. So our time is over today. So what we have understood is that whenever you are making a device design, okay, आपको क्या करना है? Industry will go for an kind of sort of a fictitious value. I shouldn't call it fictitious. It's like an overestimated value of Vt dash, which will help the longevity of the battery, it will help the longevity of the circuit rather than the exact accurate variation, accurate value. Understood? In our next lecture on Thursday, we will finish this off. I wanted to conclude it today. So in our next lecture, what we will do is we will find out that industry will not go by this calculation exact value. They will also do a very simple trick like this threshold voltage as I have shown you, simply by taking that linear slope. That is not accurate one. Theoretically, the maximum GM point, this Vt is the correct one. But in fact, the erroneous or incorrect Vt, that overestimated Vt is actually helpful for the IC. May not be theoretically correct. So if I ask the students, find the threshold voltage of the device, they will actually calculate this. And if they tell me this one, I will give a incorrect and I will give you 0. But industry will always go for this because that will help the IC to perform even after 2-3 hours. Similarly, in case of this also, we will see it in the next class, how industry will actually overestimate the TPHL and TPLH values, overestimate with respect to what we are calculating. The accurate value will always be less than the value which is recommended by industry. And then, for example, over here we found out why the Vt overestimation is helpful from an IC point of view. Similarly, we will see that how TPHL, TPLH, the simple trick which is done by industry is actually helpful from the IC point of view. Even though the exact circuit analysis will give you certain lower values. Okay, uska bhi ek karan hai. Over here, the reason was it should last for at least 3 hours. Okay, so here also there is a particular reason, we will see it. Okay, I don't want to continue this anymore. There is a lot of mathematics and all. This physical insights and all we will see in the next class. Okay, that's all for today. Thank you. So yesterday we already, I'll just stop the recording now.